This is a problem on resistors in parallel. It's a relatively slightly easier in the sense that there is these all three resistors are the same. So in that sense, from symmetry, we know that whatever happens in one of them will happen in the other resistors also. But let's follow through this discussion. So we have three resistors connected in parallel, and in the beginning, we are asked to find out what is the equivalent resistor. So that's same as asking what's the single resistor we would like to connect to the same battery, which will pull out exactly the same amount of current that's coming out of this battery in the main circuit. So that's the current I that comes in, but this current I is going to distribute itself into I1 here. Let's call that, even though the same resistors, let's pretend it is R1, R2, R3, and that's I2 there, and that's I3. And since charges are conserved, we have the relation I is equal to I1 plus I2 plus I3. And the equivalent resistance, we have concluded separately elsewhere that in parallel, they have the relation that the inverse of the resistances add up. So it's 1 over R1 in principle. So let me for a moment say this is 1 over R1 plus 1 over R2 plus 1 over R3. But all these resistances are the same. So that's the same as 3 over R. 1 over R plus 1 over R plus 1 over R. That's 3 over R. And that, when inverted, gives us equivalent resistance as the resistance of one of the resistor divided by 3. Notice that the equivalent resistance in parallel is always less than the smallest of the three resistors. In this case, they are identical, but it's still smaller, and it is smaller by a factor of 3. So equivalent resistance is R over 3. That allows us to calculate the current that's being pulled out of the voltage V. But we'll come to that in part C. So let's proceed and go as the problem is bringing out the discussion. So problem in part B is determine the voltage across each resistor. Voltage across each resistor will be the same as the voltage between these 2 points. That's V1. So that will be V1, let's say. That's across, so that's equivalent to saying how much energy is needed per electron to go from uh, the point marked here to point B. So that's V1. And the same thing about V2 and the same thing about point 3. But all those are exactly the same as the potential difference across the battery because this is all connected by the same wire. In a conducting wire, the potential is the same between any 2 points. So the potential difference between anywhere between the top wire and the bottom wire is the same. That leads us to conclude that V is the same as V1, so that we are saying potential difference across the battery is the same as the potential difference across each of the resistors. Even if this was R1, R2, R3, even that holds, and it is V1 is equal to V2 is equal to V3. It does not depend on whether the resistors are identical or not. That plays an important role in resistors in parallel. If the voltages are the same, the distribution of the currents is decided by so so let's come to part C now. Determine the current passing through each resistor We are interested in I1, I2, and I3 locally for each of the resistors. Ohm's law is obeyed. So we have I1 is equal to V1 over R1. Notice that this is the voltage across the particular resistor we are discussing. It is not the voltage that's coming out of the battery. In this particular problem, of course, they are same because they are connected in parallel. So V1 is exactly equal to V. And that allows us to complete this calculation for current. So once we know that this V1 is the same as V, we can proceed to say this is 10 volts divided by R1, is all the same resistors, so it's 300 ohms. So that gives us an answer in amps. So 10 divided by 3 is 3.33 to 3 digits into 10 raised to minus 2. So I write that as 33.3 into 10 raised to minus 3, which is in milliamps. So that's a current passing through the first resistor, but they are all identical. I2 will come out to be the same. It's V2 over R2. But that's pretty much the same. So that's I1. So that's 33.3 milliamps. And I3 also is 33.3 milliamps. We could have also calculated uh, the same number using symmetry. We would have said I is equal to, we could have also said since I is equal to I1 plus I2 plus I3, which is because they're all identical, that's the same as 3 times I1, and then use the equivalent resistance to calculate I. So, so I is equal to the voltage across the equivalent resistor, which is the battery's voltage, divided by R equivalent. That's equal to 10 volt divided by equivalent resistance, which is R over 3. So that's R is 300 divided by 3. That's 100 ohms, and that gives the number as 1. So 10 divided by 1, so that's 10 raised to minus 2. So that's about 100. 3 digits, so it's 100 milliamps. And if total current that is pulled out of the battery is 100 amps, then I1, this is consistent with the fact that all three add up, 33.3 plus 33.3 add up to 100 to 3 digits. So either we could have gone this route or we could have actually calculated the individual currents because we know that the voltages are identical. Once we have the currents and voltages known, we can calculate the power in each of the resistors. Again, because currents are identical, voltages are identical, so power will all be the same. Power P1 is equal to P2 is equal to P3. So using the values for currents and voltages in the first resistor, it's I1 times V1. It's always a current times voltage is given as the power. So that's equal to 33.3 milliamps. That's 10 raised to minus 3. So 10 raised to minus 3 amps, and voltage is 10.0 volts. So that's about 0.0 So 10, so it's 0.333 amps times voltage is watts. Watts. That's a power consumed by each of those resistors. Power is how much energy is lost per unit uh, seconds in this case, or per unit time, as the charges move around in it, and they are identical because the currents and voltages are the same. Let me stop sharing here and then stop recording again.